Um, okay. I think ready to go here. All right, so additions, I guess. Do people know what the problems are? I mean, can they go online and make sure that they know what is assigned versus what's the discrepancy problem? Or is it
I
not?
think it's just like a section off.
A section off?
So like you have it listed as like 1.5 or like whatever. Everything that's listed in your section 1 is in my section.
I see. So if you, and this is the actual print book versus the online.
My book has like business.
Oh, weird.
I have a different online version that has the section 1 with the.
Because don't you just have like a PDF?
Okay, so this is what I have. I see. So the first thing is this fields business, right? This is the one I'm going off of based on how I'm assigning it. So I guess shift up. And again, if you did this and you didn't hear it, and you were off by a section, I'll just look at what you did and give you credit for what you did. But I'm gonna stick to the ones that I got here. It is kind of strange if it's the same edition and there's different versions of it. That's confusing. Sorry about that. All right. So, questions? Questions? Oh. Go home.
I'm trying to think of one that's worth it.
Huh?
I'm trying to think of one that's worth it. I don't want to give you one that's like easily solvable.
Oh, you give them all. I don't care. Let's just let's just do them. Let's do something.
I had a quick question that we probably don't have to write down for 1.2, I believe it was.
1.2.
Yes, so for the inverse of the mods, is it just equaling 0 then? Or like whenever we do the inverse, will it equal 0 for the remainder?
So the inverse of 5 mod p is going to be the multiplicative inverse. You're looking for the number that when I multiply by 5, I get. Okay, let's do it. Okay. 5. This is what they're asking for, not the additive inverse. The additive inverse will be -5. Or what? Say something, Nathan. I'm sorry, I like to speak.
Sorry, yeah, the speaker echoed. It just said recording in progress. That wasn't me.
That's amazing. You're very loud. You're the voice of the Lord here coming through. I'm turning you down. Sorry, buddy. Okay. All right. Sounds good. Now you feel free to speak at will. All right. So
Okay, is this volume good?
Yeah, you're good. You're good. It's not your problem. It's our problem. We've got a very, I don't know, someone's listening to loud music here or something after hours. Okay, so let's go mod 7. 5 inverse mod 7. I don't know. I don't know. What do you think?
Well, according to the book.
Don't tell, no, well, okay, come on. Like, let's not go, like, let's not read the book. What do you mean, according to the book, what were you gonna say?
Okay, all I was gonna say was, according to the book, by trial and error, you can take some A, into, some power, and eventually you should arrive at the multiplicative. So like, 5 inverse should equal 5 when it's raised to a certain power.
That's true. That's absolutely true. You can start taking powers. But you're really, I mean, you are looking for the solution to this equation. Right? It's an equation, 5x equals 1. Mod 7. So I like start just going down the list. I mean, 5 times, I mean, 1's not going to be it. So 2, I'll get 3. I mean, 10 is congruent to 3 mod 7. 3, I get 15, which is congruent to 1 mod 7. So I'm happy. Right? And then with 11, it's kind of clear, right? Nine?
No.
6? 6 times 5 is 30. Close.
Or I was going, 5 times, or 6 times.
I'll get back away from 9. What's wrong with 9? I was thinking 9, right? 44 is a multiple of 11. So you go up when you get 45. Like 9. Right? Is it good? Should we do 13 too? No?
When you do it with one, then the rest kind of follow the same line.
Well, okay, yeah. I mean, there's kind of like a thing. Yeah, with 13, I think of 26. Right? 26 is 1 away from 25. So 5 squared is almost going to be 1, right? But it's not, it's negative. Right? 5 squared is or 5 times 5 is congruent to negative 1 mod 13. But that means I can square that. I'll get 1. So that means that it's 5 cubed is the inverse. Follow me? Or negative 5, if you want. Which is going to be what? 8? Yeah, that's my logic, but you could have done it a different way. Five times 8 is 40, which is 39 plus 1.
So how did you think of 8? Like, I get that would equal 40. So later was 15. How did you?
So as I said, I started thinking of multiples of 13, and I thought of 26 is close to 1, or 25, it's close to 25, right?
Mhm.
So I'm like, okay, well, so that means that, so a good guess for me is 5. So I say 5 times 5. What is that, mod 13? That's a negative 1.
Okay.
Right? So if I square everything, I'll get 5 times 5 times 5 times 5, which is 5 cubed, is 1. So now I've got my inverse. Now I just need to kind of simplify it. Well, 5 cubed is negative 5, because 5 squared is negative 1. And then negative 5 is 13 minus 5. I want to put it in the, right, so that's 8. you get, you have too much time on your hands, you start doing this kind of stuff. And then yeah, not really useful. But okay, and then 17, 17 is pretty obvious, right? So, huh? That's true. But I want to think of something one less than a multiple of 5. So if I multiply it by 2, I get 34, right? And then 5 times 7, 35. So I like 5 inverse equal 7. Right? Like 35 is kind of 1, 9. I think it's okay. Right? But you could have done that, and then you could have squared it, and then you'll come around to it, right? But what you're looking for is this solution to these equations, right? You're looking for this x that solves these equations. That's the multiplicative inverse.
Just out of curiosity,
Yeah.
so this has actually no bearing on like the holistic self-finance. How exactly is it that Law theorem relates to actually finding the quantum theorem?
How is it that what is the solution to congruence? Sorry.
So not necessarily the solution, but a solution. For mod theorem,
For what theorem?
for mod.
Fermat's theorem.
Yeah, there.
Little theorem, I assume.
I think so.
Yeah, the big theorem is pretty big, right? You guys know that story. Anyway, if you don't, well, I'll tell you about it. You mean right. So you mean like what like okay, so you mean this for prime? Is this what you're saying?
Yeah.
Okay, what about this theorem?
Well, I'm wondering exactly how you actually even came to the conclusion that this was all with congruence, because I'm really only asking because it was like a question and that's one of the exercises.
Yeah, that's a good question. This follows immediately from Lagrange's theorem and from the fact that we know the Z mod P is a field. Right? I mean, that FP is a field. So FP, let me quickly answer the question. I love questions that are not directly related to the homework. No one else likes them. Is the group, right? This is what we're saying when we're saying FP is a field. And how many elements does it have? Well, FP, the multiplicative group of the field is everything except the origin, everything except 0. So this has P minus 1 elements. The group with P minus 1 elements. Now, Lagrange's theorem says that the order, well, it says every subgroup has order that divides the order of the larger group for finite groups. Now, you can then use that to say the order of any element of a group must divide the order of the larger group. So if I take any element, so if x is not equal to 0, that means that x is in here. And then we can say that means that x, the P minus 1, is going to, well, we have that the order of x divides P minus 1. And so x to the P minus 1 will equal 1. Mod P. When I write mod P, I'm just saying that I'm in Z mod P. So I don't have, I mean, you can think of this as as being an equality inside of the group here. That's true, generally. And then if you want the kind of the usual, this kind of picture of Fermat's little theorem, I just multiply both sides by x. Because for 0, of course, this is not true for 0, but if you multiply by x, then it's true even for 0. So then you get that. So this is really, Fermat's little theorem is really just Lagrange's, application of Lagrange. Okay, homework? Everyone's happy with homework?
Can we do 3.5, please?
3.5. Yes. Let's see. Have to tell me if the 3.5 is 3.5. Ah, this one, yeah. So there was a question about this. This is a good question. I like this question. All right, so this one does rely on sort of this proposition I talked about today in lecture, which said that you can, if you have a linearly independent set, you can extend it to a basis. Or at least that's the way I was thinking to solve this. There's a stupid, okay, so there's some like elegant way of actually writing this down, but I don't want it because it's confused. It uses technology we don't have. So let's let W1. So we have a finite dimensional vector space, subspace of Fn. So it's a finite dimensional vector space. And so let's say we choose M vectors. Let's say this is basis for W, which is contained in Fn, which is equal to B. And let's extend this the basis for B. W1. So we've got these guys. We can extend by adding n minus m vectors. This is theorem. We can do this by, sorry guys, I'll come back. Blah, blah, blah. Obstacle. This proposition. I have a finite subset that spans B. This is actually more specific. You can just grab onto this. I mean, in other words, if you just take S to be any basis, really. But okay, you say L is an independent subset of B. One can obtain a basis of V by adding elements to L. So this is more specific. It says, okay, you can even just choose a basis S, say, for example, and you can do this. But what I said is possible. You don't have to prove that it's possible in your exercise. You can just refer to this theorem. The proposition 3.4.16 says that what we're doing is legitimate. So that's actually kind of that proposition is sort of an important one if you're going to do some more work with vector spaces. Okay, so let's say we have this setup. So we've got a basis of W and we've extended it to a full basis of our vector space V. Now claim. So now we can make these column vectors into a matrix A. So remember, we're not the setup of the problem is not just an abstract vector space V, we actually are dealing with column vectors. Okay, so we can make this into, each one of these we can make into a column, I mean, put them to a column. B1, B, and minus. This is not just any old matrix, this is a square matrix, an n by n matrix, right? The columns have length n, and they're, since it's an n-dimensional space, since I've got a basis, I know I've got n vectors in the space. Square matrix. So note, A is vertical. Now, there's probably something in the, there's probably something in the section that you could actually just say, section says so. I don't know. I haven't read it closely enough. Because I kind of like look over what I want and I take it out and then I put it in the lecture. For this particular section. Or you can prove it easily, right? This is not a hard thing to prove, right? Why is A invertible? Okay, good, right? That would be good, but that one is going to be hard to, that's going to be a hard technique to use in this case. That's true, but in this case, you want to kind of think about this more along the lines of, look at these columns. They are a basis, which means if I form linear combinations of the columns, I can get any other vector I want in Fn. In particular, but here's a parenthetical argument. We know, like this base, you remember these guys, EI? There are zeros everywhere except on the ith column, we put a 1. Right? This is equal to some sum. I won't, okay, I'll write it this way. No, it's going to be like sorry, W1. I'm just trying to get the, it's always a question of like, you know, switching whether or not I'm going to switch rows and columns for you. A and oops, need a I. In other words, okay, so what am I saying? I'm not saying I'm using, what my brain is trying to do is give some notation that's going to be consistent here. But I'm not saying anything here, except that it's a basis, except that these guys form a basis, so they span everything, which means I can form, for this vector, I can find some linear combination of them that gives me this vector. Right? Span, so there's some linear combination of these guys that gives me this vector. And so I was just trying to think of what's the best way I can write down these coefficients. But once I do that, you can check that, oh, I shouldn't have written A. Let me write B since I already have A. I'll relabel those coefficients B. If I look at this matrix B, B1, 1, all of these coefficients I can assemble into some huge n by n matrix. You can see that that means this is an inverse of A. Because what you're doing when you look at something like AB, right? is you're taking this column and you're multiplying this times this vector plus the next one times the next vector, and you're adding them up. And what you've got here is you've got that should equal, the vector 1, 0, 0. And then on the second column, it should equal 0, 1, and so on and so forth. It should equal your EI vector. So you get this, that this is the identity. All right. So I think you probably could find this. This probably is in the section somewhere. That if you have a basis of column vectors and you put them into a matrix, that matrix it's invertible. It's an if and only. It's an if and only. Okay, but there's the argument for it. Okay, so it's invertible. So now let's take its inverse. We'll call it B. Say B is inverse. I don't know why I'm calling it B and not A inverse, but I am. Then, and now look at the fault. Now ask the question for B times A. So then, well, actually, ask the question for this matrix. B times W1, W2. And I'll just stop at WM. In other words, this is like an augmented matrix A, but now just kill all of these guys. Just look at B times this. What do I get? Well, you'll get just the part of the identity, which is 1. You guys tell me what you expect. 1, 0, 0. But you'll stop at M here. This will be an N by M matrix. It's M by N. And then you have this part, which has N minus M. So now what I ask you is, what about this matrix? What about this matrix? So let's say this was what we started with. Can you say that this is going to be, that if you take the span of those columns, can you show that that is in fact the null space of a given matrix? You know what I'm talking about? Is it crazy? Is it hard? Consider W prime equaling and these guys. There's M of them. What is it? It's A1. I don't want to use A. Use C this time. C1 through CM, and then 0, 0. CI or anything. Your field. Can you prove this problem for this space? You solve this problem for this space. This is the null space of a matrix. If so, what's the matrix? Yeah.
Can you remind me what a null space is?
Null space is just, so it's a set of solutions to the matrix times that thing equaling 0. Set of solutions to, I've got too many labels here, so let me call it Nobody knows. Okay, let's say D. Yes. FM. D is some matrix. Matrix, so it should be something by M matrix. Depends on, so what the size of the number of rows in it will depend on the dimension of W. But let me ask this question. I think this is, hopefully this is an easier question than the one you're given. This is a hard question. I'm not saying it's a super easy question. Meant to think about it. And maybe the way I'm giving may not be the best way, but I think it's pretty good. So, but the question stands. Look at this subspace. And you give me a matrix that gives me this as the null space.
Just have like double three variables in the matrix. Would it just have three variables in the matrix?
Three variables. Oh, three variables. Yeah, I guess there's three. I don't.
Well, I was just saying that since you had like one on the diagonal, but then there's going to be some rows without one.
They're free. They're free. There are a lot of free. I guess. I don't know. I don't know. Give me a matrix. Don't tell me about free variables. Give me a matrix. I don't want little asterisks. I want, so give me a matrix that will send anything in this thing to zero. Give me something like that. So first of all, what's the size? What is the size? It has to have n columns, right? So let's get a picture. It's an n columns. What do I want? I want anything that looks like this to go to zero. So these n minus m, they're all zero. But the first m, or anything I want this to go to zero. Like, tell me a matrix that will do this.
I mean, if you have all zeros.
Okay, if the whole, so that's true. If I have the zero matrix, this will be true. However, if I have the zero matrix, I've overdone it, right? Because now it's not the null space, it's contained in the null space. I want it to equal the null space. Right? I want it to equal the null space. So you did too much. But I agree, there should be a big part that's zero.
The rows from 1 to n will all be zeros.
Okay. Not the rows. Columns between 1 to n should be zero. Because you want this times this to be zero, right? Plus this, you want this whole thing times this part to be zero. So if that whole thing is zero, you're good. And then you said whatever you want over here. Well, zero is something I can put over there. That's not what I mean. What if I want zero? That's not what I want, right? Not whatever you want. Not whatever you want. That's too loosey-goosey. Let's do something a little more precise. Sorry, I have young children. What I said?
Would you be able to put, instead of this part would be like the W one, would you be able to put the B? The rest of the diagonals with the one?
I like it. One, let's make this the identity. if I do that, I know that I have n columns because this is an n column vector. So I know here, this tells me that I should have n minus m left. And if I put the identity, that tells me actually the number of rows too. I should have an n minus m number of rows. So if I put the identity here, then certainly this vector will satisfy this equation for any c's that I want, as long as this part is 0. Because and furthermore, if this part is not 0, then, well, what this matrix multiplication does is it takes this part and it sends it and it replicates it right here. So if this is non-zero, so is this. It's the same thing, the same part. That says that the null space is precisely this W prime of this matrix. Okay, so great. We found for W prime, we found a matrix that gives us W prime as null space. But the point of what I did earlier was I took my W that they give me, an arbitrary W, and I essentially rotated it so that it would be W prime. That's what by multiplying by the inverse, I sort of said, okay, this is my W, W1 through Wm is the span. Now I'll hit it with B, and I'll get this. I'll get this space. I look at the span of these guys, I get precisely this. I'm sorry, I've been writing it. I'm sorry, guys. I should write this as a column vector. I wrote it as a row vector. Hopefully you understood what I meant by it. C1. Sorry. I wrote this as a column vector. So now I claim W is the null space of D times B. Basically, as I said, what B does is it sort of rotates W to W prime, but it's invertible. It's an invertible operation. I can go backwards too. So since W prime is the null space of D, W will be the null space of D times B. That's the basic argument. But that's the claim, and the proof is, well, certainly W is contained in this null space. Just by what we did. Right. Because B times any vector, Wi, any of the basis vectors, this is an element of W prime. So it's D, capital D capital D of anything in W prime equals 0, we're good. Just using associativity. Any of the Wi's in our basis for W is in the null space. But then you can do the converse just using the invertibility of B. Making any sense to you guys? Or is it just like gibberish? It's quiet.
Like after you made
I made the what part of the matrix? The n minus m?
yeah, so immediately after the identity.
Which part? Here?
Yeah, so,
So-
I basically was off the explanation after the identity.
after this portion. So I'm making a claim. If you believe this, so this I believe I showed. So you're saying that I'm saying W prime is equal to the null space of D. If you believe that, then I guess that I want to make this claim that W is the null space of DB. And the point is that W prime is B of W. That's basically the point. And B is invertible, so I can go back. So what I'm saying is I want to show a double containment. So I said certainly W is contained in this null space by this argument. Because any of the Wi and W prime, or any of the Wi and W, any of the basis vectors, they get sent to W prime, and then when I hit them with B, I get 0. But now you want the other containment. So conversely, if B is in the null space B, then well, then B inverse B is invertible. I've got an inverse, which is this is A. But is in null space D. Right. Which equals W prime. And so right, but then right, but what is B inverse? Okay. But I guess what I want to say is, but the inverse of one second, guys. Confused. Okay, I confused myself. Sorry. Oh, what am I saying? Not B inverse. That's why. Sorry, you guys should correct me. Obviously, this is right. Not B inverse, B. If V is in the null space of this, then B of V is in the null space. Right, not B inverse. Sorry. Right, because I mean, what does it mean? This is the null space is when D times something equals 0. But if I'm saying B is in D of B, the null space of DB, then it's then B of V is in the null space of D. D of B. Does this make sense now? Okay. It doesn't make sense. So let me show you. So I confused myself and then confused everyone else. So if V is it, then what's the definition? Then dB of V equals 0. That's the definition of null space, right? Which implies D associativity, dB equals 0, which implies BV is in the null space. Sorry, I confused myself. But that's equal to W prime. Okay, good. Okay, but now what I wanted to say was, okay, well, but. But. This implies V is in B is an element of W. Why? Because of this. It's how we define V. Inverse of this matrix. In other words, you can hit this with, you can hit anything in, so say, let me just write it this way. So say, PD equals C1 Cn, then B C1. Oops. So B equals this is equal to B. In other words, if I take a combination C1 of these rows, or sorry, these columns, C1 times this plus C2 times this plus CM times this, it's the same, I can do the same thing as taking the combination C1 through CM of these columns. That's what I get here. And if I do this and apply B, well, before I apply B, I'll get this. The other way of thinking about it is apply the vector C1 through Cn to both sides. So in other words, this equation comes from multiplying on the right by this vector C1 Cm. Just this M column vector. This is this equation. With a B on the right hand side. Then I can take the inverse of both sides and I get this. But the point is that this is a linear combination of guys in W. So this is B is in W. Okay, there's a better way of doing, there's a better way of doing this by using the dual vector space, a much better way. But we haven't talked about dual spaces, so I don't want to do it. So this is a little cumbersome, but it's, well, okay. Clean up the argument, for all of you at home, clean up this argument. It's a little bit messy. Obviously, I kind of putting it together as I'm going along, but this is the basic idea. Other thoughts? A couple other questions? After that, wonderful experience, I'm sure everyone wants more.
People always be because we were able to take like the basis vector from point of view.
B?
Yeah, did we take the basis vector of V or W?
You took both.
Oh, well,
Wait, we started with a basis vector for W, our basis for W, and then we extended to a basis for V. But then by doing that, we are allowed to then get an inverse, which allowed us to define this matrix B. B is the inverse. And then we use B to basically rotate W to W prime, where we knew it was a null space. And then that last part of the argument, which is, I kind of, didn't say very elegantly, made some mistakes, but you can fix them. It's just to say, well, once you do that, you can just kind of say, well, if W prime is the null space of D, then W must be the null space of D because it's an invertible operation. Now, let me just say, geometrically what this is asking over the reals is it's saying if I have an m-dimensional space inside of n dimensions, then is there an orthogonal complement that is n minus m dimension? The dot products, so that this is precisely sort of perpendicular vector space. That's what it's asking, to show that there is such a space. Because if you're saying that something's a null space, you can basically say, well, then the rows are going to be essentially orthogonal vectors, and that they span the orthogonal stuff, the orthogonal complement. You could do something geometric over Rn to actually, some Graham-Schmidt kind of thing, to get some orthogonal basis. However, you can't actually do that over arbitrary fields, but there's a sort of, well, you can, but you can't do it like an orthogonal. You got orthonormal, you can do an orthogonal. So anyway, there is some geometric content to this as well, which is saying, you're kind of getting complementary subspace, orthogonal subspace. But yeah, so it's important, but it's kind of, sorry, this is not the best presentation, but it should be, everything in here is okay, and you just have to kind of smooth it out. Other
Do we
questions?
need to, sorry, do we need to prove that A is invertible still?
No, you don't need to prove that. I mean, I think that this is kind of has the proof here. It's to say, because that the standard, it's basically saying that the standard basis vectors, these guys are in B. We've got a basis of B, so we can find some linear combination. Once you know that, you can assemble these coefficients into this matrix B. And then when you do that, you see that in fact, you've made the inverse matrix. So that's kind of a proof. And I think there's probably something in the I can't imagine there's not something in this section that doesn't say this outright, that if you have a basis, then and you put them into columns for Fn, that it's invertible, if and only if it's invertible. The column vectors of a matrix are a basis if and only if that matrix is invertible. We do the same thing with rows. That's another, you said this about elementary matrices. This is another way you could characterize invertible matrices. Other columns are basis, form of basis. So I would look in the book and see if that's there. It's sort of like you can think then of the fact that you have a unique solution to an equation AX equals B as precisely saying that these vectors span and that they're linearly independent. Like there exists a solution because they span, and the uniqueness of that solution is the fact that it's linearly independent. So all of these things are sort of the same kind of statement, but just cast in different ways. Short answer, no, I don't think you need. I'm happy when I'm grading this to just see. You can just say it's invertible. I think that should be. If you have a theorem you can cite, that'd be great. Or proposition. Other questions? Was there nothing else difficult? Which one was?
No, I was saying that one, that did was probably the worst.
That was the worst, and that was probably the worst solution that I could. give it. So I'm sorry. I really am. I feel bad. Like, this is not, using dual spaces is really clear. Like, you know, the orthogonal is like a clear thing you can define with dual spaces. And so once you have that and you kind of write down a dual basis, it's like immediate how to do this. But it's kind of, I don't have that in this class, so I had to be kind of messy. I didn't have to, but I will. Yeah, Gail? You happy?
I feel like I shouldn't be.
You feel like you shouldn't be happy? That's awful.
I feel
You
like
should
I-
be
I
happy.
feel like I should have more questions, but I can't think of any.
That's okay. Did I give any, I hope I gave some computing with basics.
I'm here for two.
This is probably, I would say, you know, this is, I would do some of these exercises just for fun. These are going to be like the ones that you would use the most outside of this course. Right. Like taking something from this course, aside from some basics on group theory, depending on what you do. Yeah, like change of basis is going to be the most frequently applied thing that you get from this course. Because, you know, you can use it in computer science, you can use it in all kinds of modeling. I would say it's a very, very useful thing to understand how to do this.
I do have one more question. It is a very short one, so I think that this was. That's when. What you're talking, I think it'd be section one.
What?
Yeah, I just wanted to make sure.
I think Matt asked about this too. On 9?
Yeah, so just to make sure, is the order that they're referring to, kind of like the order that we were doing back during the group section?
Yeah, well, it's not kind of like, it is the same. So this GL2F7 is a group, finite group. Right, because F7 is finite, so matrices with entries in F7 is also finite, any size. It's a finite group. So you're looking for what is the smallest integer, positive integer, such that this equation is satisfied. For the first case. What? N. But this has a formula that you, I think, have already derived.
I'm pretty sure that.
So what is the order? No. This is GL2F7.
Oh.
So what's the order?
Is it 7?
7. Yeah. You want this to be the identity, so you want this to be 0. N is 0 mod 7 when n is 7. Small is not, you know. Of course, you're not going to take any. Yeah, n is greater than 0. So then, you know, for 2, you're going to take this. You want to know what when you get this, but okay, oops. So the question is when you get a solution, what's the smallest integer n, positive integer n, when you get 2 to the n equaling 1? No, you're not allowed to say 0. For shame. Not allowed to say 0. Zero is, anything would have order 0 if you were to take negative 0 power. Order is a positive integers. So 2 to what power is going to give you 1? I'm multiplying your powers. 3. 2 cubed is 8. I'm going to 1. Very good. Here we go.
All you keep in mind that, this is,
Well, don't always keep it in mind. Only keep it in mind if you're working in GL2 of F7. If you're working in GL2 of F19, then you have a different story altogether.
Okay, rather, keep in mind the parameters that are being supplied.
Keep in mind what field you're working over. Keep in mind what field you're working over.
Okay.
Because you work over different fields, you get drastically different behavior. And I mean, characteristic 0, you know, of course, these are going to be infinite, as I think was mentioned, right? If you have, you know, a field like the rationals or the reals or complex numbers, these are going to go on, you know, they're infinite. So it's only when you're working finite, and then everything is dependent on the characteristic. In the first case, in the second case, it's very much determined by the characteristic. Okay, guys, are we happy?
Yeah.
Nathan's happy. Maybe. Okay, guys. I'll see you on Monday. Have a good weekend. Try not to pay attention to my solution. Thanks, Nathan.